All right, so our next test is a week from today, next week Tuesday. So it will cover 3 chapters, 6, 7, and 8. And so to give you a little bit of a plan for this week, today we're going to finish talking about chapter 8, go through some of the examples. I have some more examples for you. And then what I'm planning on Thursday is not starting chapter 9 yet. We're going to wait until after the break and come back to chapter 9. Thursday I'm going to go over some review of all 3 chapters. And if you have questions, specific questions about them, come prepared and I can answer those questions. And so it'll be a little bit less formal on Thursday, and we'll do some reviewing. I think Sandeep will also have his usual Monday evening review as well. So hopefully we'll be prepared for this exam this time. Okay. Any questions on that? Okay, well let's keep talking about alcohols. We've talked a lot about different things about alcohols and how to prepare them, some of the reactions with them, and we're going to continue discussing that today. But to remind you some of the things we talked about last week. Alcohols we can make in a variety of ways. One of them is from the carbonyl compound. Okay, and chapter 9, by the way, although we're not starting it, it's basically all about aldehydes and ketones. And there's a lot more chemistry. One of the main things we can do with carbonyl compounds is take this functionality and add nucleophiles to it in the form of either an H- to reduce it to an alcohol, or in the form of a carbon nucleophile. We've seen Grignard reagents. So recall there are different kinds of carbonyl compounds. Those that have just carbons and hydrogens attached in these positions next to the carbonyl, and those that have other heteroatoms like oxygen, nitrogen, things like that. They have generally different reactivities. So anything that has carbons and hydrogens, R or H, those are aldehydes and ketones. And those are more reactive. Oops, I can't spell. Aldehydes and ketones. Those are more reactive than other carbonyl compounds. So because of that, we can use less reactive reducing agents. If one of these groups attached next to the carbonyl compound is an oxygen in the form of an OH, a carboxylic acid, or an ester, or we'll see later on things like amides. There's lots of different derivatives of carboxylic acids. So things that have some other heteroatom in this position. Those are a little bit less reactive as electrophilic species. In other words, that carbon is less positive. So it takes a little bit stronger reactions species to react with it. So our reducing agents, our hydride reducing agents that are required need to be more reactive. So who remembers what those hydride reducing agents are that we use for this reaction? Anybody remember? Yeah, lithium, aluminum hydride. These are all salts of the group 13 metals, boron and aluminum. And they have, in the negatively charged form, they have 4 hydrogens attached. So lithium aluminum hydride, the other one, sodium borohydride, NaBH4. Which one's more reactive? The lithium, right. So that one will reduce all species. It'll reduce aldehydes and ketones, and it will reduce the carboxylic acid derivatives. Okay, all the way to the alcohol. The less reactive reagent, sodium borohydride, will work to reduce aldehydes and ketones, but not carboxylic acid derivatives. It's not strong enough for that. And it's a safer choice sometimes when we do that. So those are the 2 reagents that react with carbonyl compounds. Lithium aluminum hydride always will, because it's most reactive. Okay? So any questions about reduction, the addition of hydride reagents to these? Okay. The other thing we can add to carbonyl compounds are Grignard reagents. That is, we can take any organohalogen compound, when we have a carbon-bromine or carbon-iodine bond, something like that, we can prepare a Grignard reagent from it. And that Grignard reagent is a nucleophile. So the simplest example would be something like bromomethane. Right? Take bromomethane, simply react it with magnesium metal. Has to be magnesium in the zero oxidation state. And that inserts between the carbon-bromine bond. It changes the nature of the carbon from being, in this case, partially positive, to the Grignard reagent, which is now negatively charged. So when we have the metal bonded to the carbon, the metal is the less electronegative atom. Carbon's more electronegative than magnesium. So this is now, you can think of as a CH3 carbanion. Okay? And that can be nucleophilic. That can react with a carbonyl compound. And it's a pretty reactive reagent as well. It reacts with aldehydes, it reacts with ketones, it reacts with esters, carboxylic acid derivatives. And depending on what we're reacting with, we either add once or we can add twice. So then we can think about that as a way to generate and synthesize alcohols where we have added carbons. Okay, so I showed some examples last Friday of strategies to make alcohols. Here are 3 more examples of alcohols that we can make using a Grignard reagent and some carbonyl compound. So I want you to think about this for a moment. Come up with some ideas on what you would add. We have to start with some Grignard reagent, which ultimately comes from a bromide or iodide, or chloride for that matter, a halogen compound, and we have to have some carbonyl compound that it reacts with. Okay, and that could be any carbonyl compound. So I'll just take this like simple ketone like this. This Grignard reagent will react at the carbon and break the CO double bond. Okay, so that's the group we added, that CH3. And then in the final step, afterwards, we just work up that reaction, treat it with some acidic conditions, and it puts the proton on the O- as the stable product. Okay, so given that reaction, what are our starting materials to make that first alcohol on the top right? What would you start with? Yeah, CH2, CH3, oops, I went forward, sorry. CH2, CH3, MgBr. So think about the alcohol bond, that used to be a double bond, okay? And so that double bond could be from was broken by adding any one of the carbon groups, but the easiest one here to add would be this one. Okay, a 2-carbon group. So in other words, if you break the bond working backwards to the starting materials, if you think about making that bond in the reaction, that means you need this as the Grignard reagent, and this is the carbonyl. Okay, so the way to make this would be starting from, in this case, what, cyclohexanone, and the Grignard reagent would be the 2-carbon Grignard reagent. Okay, and that 2-carbon Grignard reagent came from what? The corresponding halogen compound. Okay, so the bromide plus magnesium will make this Grignard reagent. This is now a 2-carbon nucleophile. That 2-carbon nucleophile will react at the carbonyl, the CO double bond carbon, break the oxygen double bond and generate that product after you work up with acid. Okay? Question?
Is this 2 steps then?
Is this what?
A 2-step?
Well, this is one reaction, but in order to generate this reagent, you have to do this step too. Yeah, but if I ask you a question, it'll be clear whether I say, should you start with the halide or start just show the Grignard reagent, okay? But yeah, I mean, those reagents are pretty reactive, although you can actually purchase solutions of Grignard reagents from the chemical company. It's usually best to prepare them fresh in the lab yourself, because then they don't decompose, or they're not decomposed, and they're the most reactive. Okay, so that strategy to make that alcohol is the best way to make it. It's much harder to make a ring by a Grignard reagent because you have to have your carbonyl compound and your halogen and make the Grignard reagent at the same time. That's difficult to do that at the same time in the same molecule. So if you were to think of backwards in this case, breaking, if you want to say make this bond by a Grignard reagent, that means you have to have the Grignard attached to your carbonyl. That means you'd have to have something like, let's see if I can draw this for you. You'd have to have something like that. And to make that in the presence of the carbonyl itself, from the halogen compound, it has a lot of problems associated with it. So that's not the best way. But in principle, you could think about making that bond too, by a nucleophilic addition, just to make a ring instead of two molecules coming together. Okay, how about the second one? What carbon group and what carbonyl compound, what Grignard reagent and what carbonyl compound would you have to have? The carbonyl compound has to be an oxygen double bond to the carbon that the OH is attached to. But what else is on there? That's the question. What are you breaking off to go backwards in this reaction? Okay, so the CO double bond has to be at that position. And there's only one carbon group on that carbon, right? There's two hydrogens right now, two hydrogens and one carbon attached. So what's the only bond you can make by making a new carbon-carbon bond? That one, right? So we have to have the carbonyl compound from the right half where I've drawn that line, and the Grignard reagent at the point from the left side. So that has to start with this 3-carbon group. I'll draw it this way because it's in the right orientation. That's the Grignard reagent. You can make a Grignard reagent from a bromine that's on a double bond. There's no problem with that. That's the one nice thing about Grignard reagents. You can have the bromine attached to an sp2 carbon, like a benzene ring or a double bond, and prepare it. That's really versatile. That's a zero magnesium metal, by the way. Now the carbonyl compound, what does that look like that this is reacting with? Yeah, you have a C double bond O, and then what else is attached? Nope, we're adding the carbon here. So what else is attached? Hint, hint, hint. Just two hydrogens. That's what else is attached. That's it. So the carbonyl compound we start with is the simplest one, the one carbonyl compound with two hydrogens on it. This is called formaldehyde, by the way. We talked about that last week too. There's no problem with one carbon with a CO double bond. I think sometimes I'm showing those examples because a lot of times students are looking for some ketone or something else that has carbons on it, but it can be as simple as one carbon to use as a carbonyl to react in a Grignard reagent. Okay, the last one. Let's take a look at that last one. We have an alcohol, tertiary alcohol. We could add several options here to add carbon as the Grignard and the carbonyl. So again, here's the carbonyl carbon that I'm highlighting. We could add the benzene rings that I've abbreviated pH, or we could add this 3-carbon group here. Okay. So if it's the case with the 3-carbon group that we want to use as the Grignard reagent, I'm going to draw right up here on the top. We could start with this. Okay. Then we add that to what carbonyl? What else is attached? The benzene rings, the 2 phenyl groups. Looks like that, by the way. The 2 benzene rings. So that would work. That would work just fine. We take this ketone and react it with that Grignard reagent, and we will get that product. Okay? The other way to do that would be to think about breaking off, instead of the 3-carbon group, we can break off one of the phenyl groups as the Grignard reagent. Okay, so in that case, what we have is the Grignard prepared from bromobenzene. Okay, the Grignard prepared from bromobenzene. Then the carbonyl group that we need to react that with to get that product would have what attached? Yeah, you're going to have one 3-carbon group and one other benzene ring. That would also work. That would work great. There's a third way to make this. How else could you make it? Well, you could use the other benzene ring. It would look exactly the same, but we could add both benzene rings in one reaction process. Okay, that means we could start, instead of with a ketone, we could actually start with an ester. So we could use 2 equivalents of the Grignard reagent with the benzene ring. I'll just write it here: 2 phenylmagnesium bromides, plus the carbonyl now has the CO double bond, but also something else that leaves, an ester group, like a methyl ester. And we have that. Because remember, when we have, when we go from an aldehyde or ketone to an ester, a carboxylic acid functional group, we now have essentially a way to add a second Grignard reagent, because that OCH3 is actually a leading group. So we add one nucleophile, it breaks the CO double bond, and you get an intermediate, but then the CO double bond reforms to kick off the OCH3. You remember we talked about that last time too, so let me just erase this on the top and draw that up for you. So if you take you take this ester and you add one of the phenylmagnesium bromides to it, you break the CO double bond, you generate that, you generate the Grignard reagent you added to it. I think this is operating here. And what's left over here is the OCH3. Okay? If this were a carbon or hydrogen, instead of OCH3, nothing else could happen. But since it's an OCH3, this bond is polarized, right? That oxygen wants to take the electron. So what happens is this comes back down and kicks that off. And you generate now ketone. Plus the methoxide ion. That just goes away. That eventually becomes methanol. And then we know from a ketone, we just saw the example of this, with the ketone, we can add a second phenylmagnesium bromide to that and get the product. Okay, so remember, carboxylic esters can react twice with the Grignard reagent, just like it can react twice with lithium aluminum hydride. Right? Same thing. Lithium aluminum hydride will add 2 H's. Grignard reagents will add 2 of the carbon Grignard reagent. So whenever you see an alcohol, a tertiary alcohol like this, where 2 of the groups are identical, see in this case there's 2 phenyl groups in that product on that carbon of the alcohol, that opens the possibility for using, instead of a ketone or aldehyde, using a ester as a starting material and adding the 2 Grignard reagents, the same thing, twice. Okay, something to reference. Yeah, ester functional group, you have a question about that?
Oh, I was asking if she said to remember carboxylic esters can react twice with ketones.
They can react twice with Grignard reagents. Did I say ketone?
I'm not sure.
They can react twice with those kinds of nucleophiles, hydride reagents or Grignard reagents. Okay, so that's making alcohols by Grignard reagents. Okay, we just talked about that a few minutes ago. This process of reduction by adding hydride, H- by these aluminum hydrides or borohydrides. In this case, I've just shown the example from the carboxylic acid, showing that you add twice. So one lithium aluminum hydride reacts, and again, you kick off an OH or an OCH3 or whatever happens to be there. And then the product of that first reduction reacts further. There's no way to stop, because aldehyde is more reactive than acid. So you get to there, it'll immediately react with more of the reagent. So this is how we make alcohols. From aldehyde with 1 step, or from the acid over 2 additions. Okay, but the opposite is possible too. We would love to be able to take an alcohol and make an aldehyde or ketone, and then make an acid from that. Fortunately, the reverse of that, the oxidation, is certainly possible. There are ways that we can do that. And we have different oxidation methods. Again, stronger oxidants, weaker oxidants that allow us to stop at the aldehyde stage or continue to the carboxylic acid stage. And those oxidations can occur whenever you have a hydrogen on that carbon that could come off to make a new bond to oxygen. Okay, so in this case, we're oxidizing because we're replacing a CH bond with a CO bond of some kind. Whether that's another pi bond or whether it's another single bond, we're replacing a CH bond with a CO bond. That's an oxidation. So in the case of a primary alcohol, okay, there are 2 hydrogens present on the carbon of the primary alcohol. So you can oxidize twice. You can oxidize to the aldehyde stage, and with the right, I'm being really generic, this just stands for any oxidant. If it's a mild enough oxidant, you can stop there. If it's a stronger oxidant, you replace that second hydrogen with another oxygen-carbon bond. Okay. But if you start from a secondary alcohol, where we have 2 carbon groups on there and only 1 hydrogen, there's only a possibility of oxidizing once. Okay, so there's only 1 hydrogen bond to replace with an oxygen bond. So the only way we can go is to a ketone. It can't go any further. There's no hydrogen. Okay, and so obviously, if you have a tertiary alcohol where there are no hydrogens at all, nothing can happen with these oxidation reagents that we're going to talk about here. Okay, so now what we just have to figure out is what are the reagents we need to carry out these transformations. Unfortunately, there are some. Your book presents a few, and I'm sorry, I do have one typo here. There should be a 3rd acetate group right there. This is a way to take a primary or secondary alcohol and oxidize it to a carbonyl. Fortunately, this reagent, which we call periodinane, is really mild. So it stops at one oxidation, regardless of whether or not we have hydrogens left. So if we have a primary alcohol, in the case I've shown here, there are 2 hydrogens here. If you start with a primary alcohol and react it with a pyridinane, here's the structure of pyridinane. React it with this pyridinane, it takes off one of the hydrogens and makes a double bond to the oxygen, and we stop at the aldehyde stage. If there's only one hydrogen there, or we start with a secondary alcohol, pyridinane will still oxidize those, but it can't go any further regardless, but it will make ketones just fine. Okay, so this is a mild reagent. I'm not interested that you memorize the structure of this or anything, but if you recognize pyridinane, that's a mild oxidant to make aldehydes or ketones from alcohols. Okay, we can talk a little bit about that reagent. It actually turns out there's an iodine in that molecule, which is at a higher oxidation state. That is the really species which is doing the oxidation. By the way, just a general principle, anytime you have something being oxidized, something else has to get reduced. Because oxidation is loss of electron ownership, right? You're losing electrons to become oxidized. Something has to gain those electrons, and when you gain electrons, you're being reduced. So any oxidation and reduction always has to go hand in hand. When we have the alcohol being oxidized to a carbonyl, it's actually the iodine, which is in a very high oxidation state. Iodine, the product, actually is what's getting reduced. It's getting those electrons that eventually are balancing this all out. Okay, so if we have this method, we also want to be able to go all the way to the carboxylic acid. And there are some stronger oxidation reagents, basically acidic chromium reagents. Chromium in a high oxidation state like chromium trioxide with acid present. That's often referred to as Jones reagent. It does oxidation, but it doesn't stop the aldehyde. If you start with a primary alcohol, you go all the way to carboxylic acid. Another way to generate a high valent chromium is actually just to use this sodium chromate instead of CrO3. These are both very similar high oxidation states of chromium, also in the presence of some acidic conditions. Either of those conditions generate reactive species which undergo oxidation, pulls that hydrogen off of the alcohol. Makes the double bond. Okay? Again, strong reagent doesn't stop. If you have a primary alcohol, you go all the way 2 steps to the carboxylic acid. How do you think this reaction works? Now, I'm not going to expect you to know the mechanism of this oxidation, because it is a little bit complicated, but it might be useful to talk about that a little bit. Okay, so if you think about what's happening when you oxidize an alcohol, in order to oxidize an alcohol, what are we removing from this? Let's say we go to an aldehyde. Just without thinking about the oxidation reagent at the moment, what have we lost? 2 hydrogens, yes. So we've lost the equivalent of an H plus and an H minus, right? That's the equivalent that we've lost overall. If you look at all the valence electrons here and at the end, then we must have an equivalent of H2, right? Hydrogen and 2 hydrogens and 2 electrons. In this process, we're not actually forming H2 necessarily. But in order to do that, we need to think about how we do that. So the electrons in this double bond either had to come from those electrons or these electrons. Okay? And just think about that, the principle of what you know about electron flow for a moment. Okay? What do you know about electron flow? I'm going to change color here so it's a little bit easier to see. If we think about the electrons flowing down from that, in other words, the OH is reacting typically like an H plus source. The electrons stay with oxygen, but let's say those electrons come down to form the new CO double bond. What has to leave from the carbon in order for that to happen? Because we can't put more than 8 electrons around that carbon. Something has to break with the electrons. It means we have to lose an H minus. Okay? That's a difficult thing to do. Usually when we are losing hydrogens, we're losing it as a proton. So you can imagine doing this process is somewhat difficult. And you can think about that exactly the same from the opposite direction. So if we think about taking the electrons in this direction, that means this is coming off as an H plus, then this would have to come off as an H minus. We have to take electrons away from oxygen. Okay, why would oxygen give up electrons? It doesn't want to, right? It's electronegative. The way most oxidations work when we go from alcohol to a CO double bond, and then eventually to a carboxylic acid, is that exactly in this kind of way. What we need to do is replace hydrogen with something that's more electronegative than oxygen, so that those electrons that's bonded to it can leave away from oxygen. That's what these high oxidation state reagents do. So for example, if in the presence of chromium trioxide under acidic conditions, we actually have this species generated. Chromium trioxide, if you protonate one of the oxygens, this chromium is very, very electropositive. Okay? It's a really reactive electrophile. So you can think about the oxygen forming a bond to the chromium, and you get an intermediate now where we generate what we call a chromate ester. Okay, and so we get an intermediate like this. Notice what we've done. We've replaced an OH bond with an O chromium bond. Now the chromium is in a high oxidation state. It's very electropositive, which means it wants more electrons. It wants electrons like crazy. So what do you think the nature of that OCR bond is? Polarized towards the chromium. And if you think about a process where those electrons flow to the chromium, and then the electrons from one of the other chromium-oxygen bonds takes the hydrogen, and then those electrons form the double bond. That's how this reagent is actually working. It's nicely set up to take electrons away from oxygen, at the same time pull the proton off adjacent so we can form the double bond. So for your information, I mean, just to put this in context of chemistry, we think about where electrons are and where they want to go to, then we can make sense of how chemistry happens. It's a pretty complicated mechanism. I would never expect you to be able to look at that reaction we've done and see that right off the bat. Nor do I expect you to be able to remember that and give it on a test or anything. But that is, if you're interested, that is how almost all oxidations happen. You have something which is replacing an OH bond with more electronegative atom that takes the electrons. Okay? Well, I have a question up here in terms of oxidations. I'm talking about oxidations of alcohols, but that's not the only kinds of oxidations we've seen so far in this class. Can you think of other oxidations that you've seen?
Hydrogen peroxide.
Hydrogen peroxide and what? On a cut. Oh, sure, that's an oxidation. Hydrogen peroxide will oxidize and kill bacteria, actually. But what about chemistry? Hydrogen peroxide oxidizes organic molecules too, so we'll talk about that in a minute. You have seen some oxidations. You've seen an oxidation where you could take something like cyclohexene plus a per acid. As a matter of fact, this was on the last exam. Let's say acetic per acid, or there's an NCPBA, metachloral perbenzoic acid. It's a per acid with an oxygen-oxygen bond. Remember that reaction? What was the product? Remember that reagent inserts an oxygen across a double bond, so you generate the the 3-ring oxygen bond, an epoxide. But that's an oxidation. We replaced a CC bond to two CO bonds. We've gone higher in electronegativity. That's an oxidation. We've seen, what did we see? We saw potassium permanganate, right? That's also a high oxidation state species. We can generate alcohols, diols. We saw that from the alkene chapter. We've seen lots of different oxidations of this kind, right? So there are some examples of oxidations. I point this out because in this chapter, we're going to talk about it in a moment, this is actually a special kind of ether. Since this is a chapter on alcohols and ethers, that's a special kind of ether in epoxide and has some reactivity. Okay, so oxidations. Pyridinane stops at aldehyde. The chromium oxidants go higher to generate the carboxylic acid. Okay. We touched a little bit on this last week too. Alcohols can react as an acid with the appropriate base. Something like sodium hydride can take off the proton and generate the alkoxide, which we can use as a base. We can use that as a good base for E2 eliminations. Or as a nucleophile, if you have a reactive alkyl halide, like methyl or something that's not very hindered, you can do an SN2 substitution reaction and generate an ether product. Okay. How many people forgot this already from last week? Well, let me remind you. So last week we talked about these two examples. Those are two ethers. What alcohol and what alkyl halide would you start with to make them? The important factor here is that you have to do an SN2 substitution reaction. And in order to have an alkyl halide do that, it has to be the least hindered possible, or the less substituted, right? So methyl is the easiest one. A primary halide would be next. A secondary halide gets more difficult. And a tertiary halide can't work at all. Nor can a benzene ring, because you can't do nucleophilic substitution, SN2, from the back side on a benzene ring. See how the last chapter feeds into this chapter? That's chemistry. So if you're going to think about making this ether, it's not that bond you want to make. That won't work, because you'd have to start with bromobenzene plus the alkoxide from this alcohol. Okay. And there's no way you can do a nucleophilic substitution on the bromobenzene. That has to be sp300 and left unhindered. Okay. So the only choice here for the choice of alcohol and halide would be to be forming this bond. So the alcohol would be this portion. The halide would be where you broke it off. So that's the alcohol you start with to make this ether, and the bromine would be on that primary carbon. That's the only way that would work to make that ether, through this ether synthesis. Okay? Same thing here. On one side, we have the carbon attached is tertiary, and on the other side, it's primary. So guess which one has to be the bromide? Question?
Question. Last week you just said like O with a negative.
Right.
Then now you said OH.
Well, this would be the alcohol we start with. To get there, we have to deprotonate it and make the alkoxide, yes.
Okay.
So just like I show up here, you do have to generate that first, but that's the alcohol we start with, and that's the alkyl halide we start with. So when I ask a question on an exam, for example, I will be specific. What is the alkoxide or what is the alcohol? So look for that if I ask that. So obviously, the only way you could do this one, you're not going to do a substitution on the carbon that's tertiary. So that's not the bond you want to make. The bond you want to make is to the primary bond. So the primary halide plus the alkoxide generated from that alcohol. Okay. What would happen if we do this? What's the product? If you take this molecule with the OH and a bromine and treat it with sodium hydride. What does sodium hydride do? Takes the hot proton off of the alcohol to make an alkoxide, right? So what happens is you generate this. Okay? Now we have an alkoxide, and we have an alkyl bromide. They happen to be in the same molecule, but they could be in separate molecules, right? And we make an oxygen-carbon bond. Kick off the halogen. The same thing happens here. But what kind of product do we make? A cyclic product. That comes from the backside, kicks off the bromine. We form a bond from oxygen to that carbon. So how many atoms in that ring? How many atoms would be in that ring? 1, 2, 3, 4, 5. That's where we leave the bond. The sixth carbon is sticking off of the ring. Okay, so we actually make a 5-membered ring with a CH3 group attached here. Okay, so that's actually the product, but I've thrown a little curveball for you here to remind you of some of the stuff that's going to be on the test next week. I have shown stereochemistry for the chiral center that the bromine is attached to. Since this is an SN2 reaction, what happens to the stereochemistry at that center? It inverts. So if the bromine is up, we start with, in this case, the S stereochemistry for that center at carbon 5. We need to end up with the R stereochemistry for the center, that carbon. So the methyl group should be pointed up or pointed down. The methyl group should be pointed down. That's the R stereochemistry. If you don't believe me, figure it out with your thumbs. Hydrogen pointing up, you need to write it. Okay, so what we learned before in stereochemistry applies to SN2 substitutions that we did in chapter 7, which is what important for making ethers like we're talking about here in chapter 8. Okay. It's all there, it doesn't go away. Okay, phenols. Phenols are a little different. Phenols don't really react with acids at all, unlike tertiary alcohols, which can form carbocations. But you can deprotonate them. You don't need as strong of a base as sodium hydride because phenols are more acidic, right? So actually, to make the alkoxide from phenol, potassium carbonate is a weak base, but it works just fine. In this case, it's an ether synthesis that I just illustrated here with an ethyl bromide, and we put that group on. Okay. Another thing that phenols do, a little different than alkyl alcohols, is the oxidation does a little different things. You can oxidize phenols, but what it does when you use these oxidation conditions like chromate, or there are other ways as well, other things can oxidize these, we end up making this interesting benzoquinone, or a quinone structure, where we have this six-membered ring, but two CO double bonds. So not only does it oxidize that bond, but these electrons here rearrange, and we actually get another oxygen put in that position. So this quinone oxidation is actually quite an important process, because it's easily reduced as well. Because what have we done in this oxidation of phenol to quinone? We've lost the aromatic stabilization. So it's pretty easy to reduce it under pretty mild reducing conditions to regain the aromatic stabilization. Actually, that other oxygen doesn't leave, you make a hydroquinone. And then this hydroquinone and quinone structure, that reduction, oxidation, it's easy to go back and forth between quinone and hydroquinone, benzoquinone and hydroquinone. Oxidation and reduction. And that's really important in biology. As a matter of fact, you all wouldn't be sitting here without this reaction. Here's an example. This is in your textbook. I don't think I had it in the notes. But in your mitochondria, which is the energy-producing parts of your cells, there's these species called ubiquinones, naturally occurring ubiquinones. And ubiquinones are part of the process of electron transport and energy generation through this oxidation and reduction. So NADH in your cells react with the benzoquinone form and reduce it to hydroquinone. There's electron transfer going on. And that's a reversible process, so that's oxidized back. So this is part of generating energy in your cells. And actually 95% of the energy we produce comes from this process. So it's an important reaction. Well, ethers. Let's talk about ethers a little bit more. We talked about how we make them. They are interesting because they do have some reactivity, although generally things like diethyl ether, which, as I said before, is that old anesthetic from the 19th century. Tetrahydrofuran, these are now commonly used as solvents for reactions because they're pretty inert to most reactions, especially negatively charged reactions, things that are under basic conditions. Epoxides are a little different. Because of the ring strain, they are more reactive than typical ethers. Okay, so we can actually use epoxides as synthetic intermediates to do chemistry with. And there's all kinds of different ethers that all have different kinds of properties. There are polyethers, part of materials and things like that. What kinds of reactions do ethers do? So if you think about water, you think about alcohols, how do we break a CO bond? If we want to think about doing reactions with ethers, we need to break a CO bond, right? Well, one way to think about breaking a CO bond, just like we break an OH bond to generate a carbocation or some other reactive species, we can break bonds by first activating it by protonation. So here's a couple of examples of things that can happen to cleave ethers under strongly acidic conditions, typically. Okay, so notice I have this ethyl isopropyl ether. Ethyl isopropyl ether. If I react this with hydrogen iodide, not much can happen until you protonate the oxygen. Once you react the oxygen with the acid and generate the positively charged species, then those CO bonds become weaker. right? So this oxonium species, by the way, that's an equilibrium typically. Any acid protonation can be deprotonated. That alcohol now has weakened bonds. Now, unless you can really form a stable carbocation, it doesn't really happen on its own, but if you have something around, like halogens can be pretty good nucleophiles. And you can do an SN2 substitution on the least hindered side. So this iodine can attack that carbon and that oxygen can break the carbon-oxygen bond to generate this alcohol and this iodine. Notice this is the reverse of the Williamson ether synthesis, right? We could take this with sodium hydride, deprotonate it, and react it with the iodine. That's basic conditions to make the ether. We can cleave it under acidic conditions. Okay, notice I have one secondary alcohol, or one secondary carbon that the oxygen's attached to here, and one primary. So when you do this cleavage, it'll always happen, the halogen will always attack the less hindered side, because again, it's an SN2 substitution. If you can form a really stable carbocation, like in this case I have a secondary carbon on the left side here, and a tertiary carbon on the right, you protonate that with an acid, you generate this oxonium species, but now we have the ability to form a stable carbocation. So that can break without the intervention of any other nucleophile, okay, or any other species. So this bond can break to form a carbocation. If you had something nucleophilic, good nucleophilic, you could add to that, but oftentimes what happens is you lose hydrogen through the E1 mechanism. So that's an E1 reaction from here to here. So not only do you form the alcohol, a byproduct in that case is a double bond. Here's a few more examples. We want to jot them down or look at the video later, but I don't think those were in your slides either before. Here are 3 cyclic ethers. We can do this with THF to illustrate reactions with various acids. So what do you think happens in these cases? Different ether starting materials with different substitutions and different kinds of acids. So if we just take something like HBr, which has a H+, which is an acid, and Br-, which can be nucleophilic, okay? That's why the mineral acids, H, I, HBr, HCl, those halogens are pretty nucleophilic. What do you think happens in this first case? First step, protonation. You form an oxonium. Now we've weakened those CO bonds. But we don't have any stabilized tertiary centers, so you're not going to form a carbocation. So the next step would be bromide doing an SN2 substitution. So which side will it do it on? Left side or the right side? On the left side we have a secondary carbon, and on the right side we have a primary carbon. Right? So what's the easiest to attack with a nucleophile? The primary. So the bromine will attack here and break the CO bond. So what we'll have is, I think I have the right stereochemistry here. 1, 2, 3, 4, 5. Remember the cyclization I showed you previously? This is a similar one, but I'm not breaking the chiral center bond, so that stereochemistry should be exactly the same. That should be our stereochemistry here and our stereochemistry here. Nothing happens to it because I didn't change that bond. I broke the other bond. So that's the kind of ether cleavage that could happen under acidic conditions. If I do the same with the one on the bottom, or the one below it, before we get an oxonium, protonate, now we have weakened the CO bonds again, but what's the difference with this one? Tertiary versus primary. That carbon versus that carbon, right? So what will happen? Count that right. Oops. You'll form a carbocation, right? They form a carbocation, and then what could happen with the carbocation? The bromine can add. So it's like what mechanism would this be? It's a substitution reaction, right? We've substituted oxygen for bromine. Two-step reaction where we first form a carbocation and then the bromine adds.
How did on the top one, the alcohol group, like stay with that, and on the bottom one, the alcohol group stayed with the other one?
Because this is an SN2 reaction, and the bromine has to attack the least hindered carbon, which is the primary one.
But isn't that what it did on the bottom one too?
In the second one, no, nothing has attacked yet. This now forms a carbocation because it's tertiary.
And then bromine.
And then bromine adds to the carbocation. So the bromine doesn't matter what the sterics are. Now it's the most stable carbocation. That only happens when you have tertiary. Okay? So again, this is a little bit of a review of the last chapter because those issues can be important in chemistry. So that's the difference. This is an SN1 reaction, not an SN2 reaction, because we have this very stabilized carbocation. In the last case, we get to the same intermediate. You form that same intermediate with concentrated sulfuric acid, and it forms the same intermediate carbocation. Okay, but then we don't have a nucleophilic halogen. So what happens with that carbocation? What do you think would happen with that? They could reform the ring, yeah, that would just be an equilibrium back and forth. But what happens if you take off one of these hydrogens? That will be taken off to regenerate the acid catalyst. And the product you form then would be 1, 2, 3, 4, 5. The double bond, that's an elimination reaction. That's where you can see some of the subtle differences between whether something goes by substitution or something goes by elimination. That's an E1 elimination reaction. Okay, the difference is we don't have a nucleophilic counterion. HSO4- that's generated when you protonate is not a good nucleophile. You can take the proton back, and it does so from here to generate now a stable alkene, but it's not going to add as a nucleophile. Question?
So that the first reaction, that the ring stays intact until the bromine
Exactly.
attacks it.
Yeah, because it's not a stable enough carbocation to break apart. And you could, well, I suppose if you heated it super high, it would, but under the conditions, you could control that. It would not. It would do SN2 only, not SN1. Because it's primary and secondary. Again, these are sort of some gray areas, and I do them to illustrate these points. Hopefully it helps you understand a little better. On the test, I'll be very explicit about, tell me about this SN1 reaction, or tell me about this SN2 reaction, or this elimination reaction. I'm not going to have you trying to guess which way it goes, I'll be explicit in what I'm looking for. Okay. Okay, so ethers can be cleaved. Epoxides, remember we can make epoxides by oxidation with a per acid. MCPBA stands for metachloropurbenzoic acid, so it's this one, in case you wouldn't know. It's just that same oxygen acid like I showed the per acetic acid before. Epoxides are strained. They're really strained. And they're more reactive than other ethers. So these ring openings, or these openings of breaking of CO bonds, can occur much more readily. As a matter of fact, if you take the epoxide and protonate it with an acid, sorry, my drawing's terrible, then that halogen can react quite quickly with this three-membered oxonium and break the bond. And it'll come opposite side. Just like when we added Br2 to a double bond, we get a bromonium and then the other bromine adds opposite. Well, the same thing happens when we have these three-membered oxonium. The halogen will add on the opposite. So we can actually, again, do a substitution. It is an SN2 reaction to generate that. So not only can you add halogen, but something like water, H2O, can react as the nucleophile and put a second OH group on. Okay, same thing. You form the oxonium, and then water attacks and breaks the three-membered ring. You get an OH on either side. Okay, pretty straightforward. As a matter of fact, I think we talked a little bit about this in the chapter on alkenes when we first introduced epoxide. The other thing, though, that typical ethers don't do, like when we generate a Grignard reagent, or we do lithium aluminum hydride reductions or things like that, we do them in ether solvents. We do them in THF or diethyl ether, because those solvents are inert to those strong nucleophiles, like hydrides and Grignard reagents. Epoxides, on the other hand, are not. Epoxides react with strong nucleophiles. Even if you heat it up enough, hydroxide will open up an epoxide. Grignard reagents will open up an epoxide. So this is another example of where we can use Grignard reagents to make new carbon-carbon bonds. So, for example, phenylmagnesium bromide reacts. Again, it's an SN2 substitution, so it reacts on whatever side is least hindered. That's why I've shown it only attacking this carbon, not the more hindered one. And so we made that new carbon-carbon bond, but instead of the alcohol being attached to the carbon that we've added on, the alcohol is one carbon further away. So this is a complement to additions to carbonyls for alcohol synthesis. We can use a Grignard reagent but get the alcohol another carbon further away by opening an epoxide. But epoxides, we can often think of them, they're not quite as reactive as carbon-halogen bonds, but the CO bond of an epoxide is certainly more reactive than typical ethers. And so we think of these as synthetic intermediates for making new carbon bonds for synthesis. So they're quite useful reagents. Okay, so that's alcohols, ethers. I just want to spend a couple more minutes and talk a little bit about the sulfur analogs. Because if we go down one row on the periodic table from the alcohols, we can have sulfur compounds. These are called thiols, as the SH, or mercaptans or sulfides if there are two carbons, the ether analogs of sulfur. And they smell a lot. They're pretty stinky. We can detect them down to parts per billion concentrations, I think. And humans are very sensitive to the smell of thiol. So methane thiol is what's added to natural gas to give it the smell. Natural gas is odorless. That's why they add methane thiol to it in very tiny amounts so that we can actually detect it if there are leaks, because then we know something's leaking and we can fix it. So methane thiol is added to natural gas. Sulfur compounds are naturally occurring, so this is a compound found in garlic. And it's one of the pungent aromas from garlic. Cysteine is an amino acid which is found in our proteins and peptides, which contains sulfur in the backbone, and that sulfur actually is very important in a lot of different ways. And sulfur is a much better nucleophilic atom than oxygen. So we go down one on the periodic table, it's less basic, but much more nucleophilic. So these reactions, similar to what we do with alcohols to make ethers, we can take thiols, make the thiolate, and react it with alkyl iodides to make the sulfides. Okay, sulfides, interesting, huh? Well, as I said, cysteine is an amino acid that's important in biology. And one of the ways that it's important is that when cysteine is incorporated within a protein backbone, those sulfur bonds can form disulfides. This is an oxidized form of sulfur, where you have a sulfur-sulfur bond. If you take two thiols and oxidize it, and there are many things that oxidize it, iodine for one, you can make a disulfide, where we now have a sulfur-sulfur bond. That's also reversible. You can reduce the sulfur-sulfur bond to make the thiol. In protein structure, some of the larger structures of proteins depend on having bridging disulfide bonds. And that leads to the function of the protein if it has the specific structure. So those disulfide bonds are quite important. As a matter of fact, it's also kind of a practical thing. In your hair, there are many proteins which have sulfur-sulfur bonds, linking them. So if you think about this as a protein strand, one protein strand and another protein strand, and those sulfurs are connected. If you go and get your hair curled and permanent, you can break those sulfur-sulfur bonds by reducing it with ammonium thioacetate. That breaks on the surface of your hair those sulfur-sulfur bonds, and then you curl the hair, and then you reform sulfur-sulfur bonds by oxidation. So after reducing your hair, they treat it with hydrogen peroxide and reform sulfur-sulfur bonds, but in a different state. So it helps keep your hair permanently curled, or at least for a while until it grows out. So that's the chemistry behind perms. So if you really want to go back to the 1980s, you can. Who wouldn't want that look, right?